Let us look at another problem from Hcverma rotational motion. This is problem number 60 on page number 199. See, refer the textbook for the statement. A uniform rod of length L. This is a rod of length L. It lies on a smooth table. There is no friction. A particle moving on the table strikes the rod perpendicularly at an end. So a particle, let us take the mass of the particle as small m. Let us take the velocity of particle as v0. It strikes the rod at one end and stops. It means after the impact the particle stops. It doesn't get embedded, it just stops. We are supposed to find the distance travelled by the center of mass by the time the rod turns through 90 degrees. The distance travelled by center of mass when the rod turns by 90 degrees. This is what we are supposed to find. So let us use the conservation of linear momentum as well as angular momentum. First, let us use the conservation of linear momentum. Suppose the mass of the rod is m and velocity acquired by the rod is v after impact. So what is the total momentum after impact? M into v. Because the particle stops, it has no momentum. What is the total momentum before impact? M into v0, because before impact this was not moving. And that gives me velocity of the rod after impact as mv0 upon capital M. Very simple. Now please note there is no friction. There is no external force. There is no friction. So the rod will move with a uniform velocity. There will be no acceleration. And same thing will happen regarding rotation. Since there is no friction, there is no opposition, and as there is no opposition, whatever is the initial value of omega, it will continue. So now let us use the conservation of angular momentum. We are going to take angular momentum about the origin or midpoint of the rod, because center of mass lies here. So what is the initial angular momentum? M into v0 into L by 2. This angular momentum m into v0 into L by 2 is the I omega. I of a rod, it's ml square by 12 into omega. That gives you the value of omega as 12 by 2 is 6 mv0 upon ml. Right, 1l will come down, 6 mv0 upon ml. This is omega and this is velocity. This is linear velocity and this is the angular velocity of the rod. Now the rod turns by 90 degrees, means theta is pi by 2. Now we know, since there is uniform motion, omega will be theta upon t, and in the same time interval v will be distance upon t, where x is the distance travelled by the rod. So what will be omega upon v? or v upon omega. V upon omega will be x upon theta. We are interested in finding x. So x will be v upon omega into theta. What is v? V naught upon capital M upon omega, so I will reverse it. ml upon 6 mv0. And what is theta? 90 degree means it's pi by 2. So m v0 capital M will cancel, and the answer will be pi L upon 12. So distance moved by the center of mass by the time rod turns to 90 degree is obtained as pi into L upon 12. Okay. Now we are going to do another problem. Let us do another problem from Hcverma only. It is a little long, big problem. Let us do that. It is problem number 68. Hcverma, page 199. Again the same chapter of rotational dynamics. Again refer textbook for the statement. A meter stick weighs 240 gram, is pivoted at its upper end. It can freely rotate in a vertical plane. So this is a meter stick. It is pivoted at the upper end, right? Okay. Now a particle of mass m, whose mass is 100 gram, there is a small particle, the mass of the particle is given 100 gram, is attached to the end with the help of a string. The string is also 1 meter, so this distance is also 1 meter, this distance is also 1 meter. They are same, both of them are 1 meter. Okay. The rod is vertical, string is horizontal, and now what is happening is the system is released from rest. Now as the system is released from rest, this particle will move and will collide. Okay. The particle collides and it sticks there. So now this particle comes and sticks on the meter stick. Now due to the impact, the stick is going to rise, isn't it? The stick will rise. So this is the final position of the stick. We are supposed to find this angle theta through which the stick is going to rise. Supposed to find what is this angle through which the stick will rise after impact. So this is the definition of the problem. Mind you, it is really a intricate problem. In fact, very rarely it will be asked in JEE mains because it is going to take a lot of time. But from the understanding point of view, it's really a nice sum because we are going to use the principle of conservation of momentum. We are going to use the principle of work and energy. We are going to use the principle of rotational motion, rotational dynamics. So many principles are required to be used over here, and that is why I have chosen this problem. Of course, we will need calculator for this because the numbers will be really complicated. So we'll need a calculator to solve this sum. Okay. So let us first see what is the velocity of the particle as it hits here. As it hits here. You know the height is h, so velocity will be root 2 gh. H is 1 meter, g is 10, so the velocity will be root 20. The velocity as it hits here will be root 20. Let me calculate the value of root 20. Root 20 is 4.47 meter per second. Okay. So what is the momentum imparted? The momentum imparted to the system will be m into v. Right? And due to this momentum imparted, the system is going to acquire a new velocity. So what is the initial momentum? The mass is 100 gram. So 0.1 into 4. My pen is stuck, just a second. So initial momentum is 0.1 into 4.47, and afterwards what will be the total momentum as the body sticks? The mass of the particle is 0.1. The mass of the stick is given mass of the stick is given 240 gram. So this is 1.3153. Okay. Now under the influence of this velocity, the block is going to rise. The rod is going to rise. So now we are going to use the principle of, again we are going to use the principle of work and energy to find out the angle. This is theta, this is L. This will be L cos theta. This whole thing is L. So this height will be L minus L cos theta. So the mass 100 gram rises to this distance. Please note that center of mass of the rod, so mass of the rod must be considered at halfway between this and this. So if the 100 gram mass rises through this distance, the 240 gram mass will rise through half the distance. So what is the net work done by the weight? The net work done by the weight, since it is in the upward direction, will be work done due to 100 gram mass, that is 0.1 into G. L is 1 only, and 0.24 into G, half of that. This is the negative work done, so the total work is negative. Of course, the kinetic energy is also finally 0 and initial is half mv square, and therefore the change in the kinetic energy is equal to work done principle we can apply very easily. So what is the initial kinetic energy? The initial kinetic energy will be half into m into v square, and this is equal to this plus this, 0.1 plus 0.12, it is 0.22 into 1 minus cos theta. Again we'll have to do some intricate calculations. To G I forgot. Now let us understand what is the huge mistake which is made while solving this example. What is the huge mistake that has been made while solving this example is that the velocity at this point and velocity at this point are going to be different because the rod is going to rotate. It's a big mistake which is done in this example while trying to solve it, and this will never give us a correct answer. So please understand the mistake that I have made. You cannot use principle of conservation of linear momentum because velocity of the rod has to be considered as a point mass concentrated at the center. So these 2 points will have different velocities, isn't it? Angular velocities will be different, and since the angular velocities will be different, we have to use the approach of, I think, conservation of angular momentum and not the approach of conservation of linear momentum. Because as the particle is hit over here, it is going to start rotating, and it will start rotating, and that is why if you have same value of omega, but you know v is r omega, so we have to consider that aspect also while trying to solve this sum. So let us use the principle of conservation of angular momentum and not linear momentum. We will use conservation of angular momentum about this point, because then there will be no torque acting on the system. Okay, so as the 100-gram particle strikes here with a velocity root 20, what is the initial angular momentum? M into V into L. Mass is 0.1, velocity is root 20, and L is 1 meter. As the particle sticks to it, it will also have angular momentum at the end. That will be 0.1 into final velocity V into L. L is 1 meter, plus the angular momentum of the rod, which is ml square by 3. Into omega. What is omega of the rod? Omega of the rod will be V upon L about this point. L is this whole distance. And this equation, L is 1 meter of course, and this will give us the velocity of this particular point, right? So let us do the calculation here. Root 20 is 4.47. So 0.1 into 4.47 equal to V. This is 0.1, and 0.24 upon 3 is 0.08. So that leaves us with a V as 2.48. So the velocity is 2.48. Please see that we cannot use here the principle of conservation of linear momentum, because the rod is tied here. As the rod is tied here, it will be under tension. There will be some reactions over here. There will be a horizontal and vertical reaction at this point. So it is better to use the principle of conservation of angular momentum about this point, because about this point there will be no external torque. So we get the velocity as 2.48. Now we'll come to the next part of it as the rod rises. Let me draw a broader diagram here for you. This is the mass 100 gram, whereas this is the midpoint where the mass is 240 gram. Now Suppose this is the height h through which the 100-gram mass rises. This is the height through which the mass 240 gram rises. So this is the height through which the mass will rise, 240 gram. Please note that suppose this length is L and this angle is theta, then up to here it will be L cos theta. So the height h will be, this whole length is L and L cos theta. So this height will be given by L minus L cos theta. As this particular length for the center of mass is L by 2, if we apply the same funda, the height through which the 240 gram will rise will be L by 2 minus L by 2 cos theta. Now we'll use the principle of work energy between point 2 and point 1. What is the kinetic energy, final kinetic energy? I will use the formula here. E2 minus E1. There is only one thing which is doing the work, which is weight. You know, as the weight rises up, the work done is negative because it is done against the gravity. So E2 is 0. That is the final kinetic energy. What is the initial kinetic energy? The initial kinetic energy will be rotational kinetic energy. So the kinetic energy is given by half I into omega square. So half moment of inertia of this 100 mass particle will be m r square. M is 0.1. R square is 1 square only. So half into 0.1 into r square. And the moment of inertia of the rod is ml square by 12. Length is ml square by 3. And omega square will be v square upon L square. L is 1 again. So this is the change in the kinetic energy. Work done by the 100 gram mass, it will be negative. Work done by 100 gram mass is 0.1 into L minus L cos theta. L is 1 only. And the work done by the 240 masses, that is 0.24. It will be half of this. Again we can put v square as, I think we got the value of v as 2.48. So I have to put v as 2.48 and let us do the calculation. Minus minus will cancel. So we'll have to do a lot of calculations again. Okay, so I've done the calculation. Here I think G is missing. G is 10. So this turns out to be 0.55. This is 0.22 into 10 into 1 minus cos theta. See what does it give us? 0.55 upon 2.2. That is 0.25. 0.25 is 1 minus cos theta gives you cos theta as 0.75. You look up the answer in log tables. There is no other way we can find a value of cos theta, but you know the range. Now suppose there is an option in the exam and cos theta is equal to 0.75, you can find a range. We know the closest values. Cos 60 cos 60 is 0.5, right? So let me write here, cos 60 is 0.5 and cos 45 is 1 by root, that is 0.7, not 7. Our answer is 0.75, so it will be very close to 45. So you must choose the answer close to 45. If we actually look up the log tables, you will get cos inverse of 0.75 is 41. So the answer is 41 degrees. So we have made a mistake in the beginning of the problem by finding the velocity using conservation of linear momentum, but since the system is rotating, we must use conservation of angular momentum and not the linear momentum.